All right, so that's the plan. Let us go back to where we left off. So the idea from last time is we had a bunch of data, and we wanted to see like, did it fit a an idea for it that we had in our mind? Did it match this model that we came up with? Our theory for how this data was generated. For example, this Robert Swain trial, we found that we were able to simulate, right? Our model was like the jury panels were selected perfectly at random, where there was this particular split in ethnicities in the jurors, and we found that randomness, like our random model that was picking jurors, did not explain properly what happened in real life, that really small proportion. And so we were able to test that. It was really cool, right? Dun, dun, dun. So we had here is our sample jury populations, 100 size jury, and we were able to use sample proportions, right, to simulate a jury. And it was really cool. We did it 10,000 times, and we never saw such a small proportion, right? We never saw it. We could make a histogram for what we did see. It's wonderful. And we did the same thing for jury selection in Alameda County. I want to move on now, and like we had to figure out like what's one number that could tell us the difference between a bunch of different distributions at once. Like this is we're trying to like find the difference between this and this together, and so we had to like make a fancy number called the total variation distance. But anyway, I just want to go along with that some more today and do some more simulations. It will be fun. So I want to talk about Gregor Mendel, who I'm sure you learned about in biology class one day. And he essentially invented genetics, right? The whole field of that. What he did, right, in his experiments was he grew pea plants. He grew pea plants, and the pea plants had different colors for their flowers. His experiment over his the whole time that he was doing this, he grew exactly 929 pea plants, and then he found that 705 of those pea plants had purple flowers. The rest of the flowers were white. Okay, and so if you do the math, 705 over 929, that is almost 75%, right? Almost 75%. Not quite, a little bit over, but he thought that this extra bit after 75% was just due to random chance. He's like, you know what? Probably nature works with like 3/4 chances. That's more natural to appear in nature than like 705 over 929 chances. That was his thought. So he's like, all right, probably that extra bit, the error amount after the 75% was just due to chance. And his model was like, you know what, there's probably just a perfectly 75% chance that if I grow a pea plant, it will have purple flowers, and a perfect 25% chance that it will grow white flowers. Doesn't matter about the colors of the other plants. All right. So that was his hypothesis. All right. That's what he thought. It's like, this wasn't perfectly 75%, but the world isn't perfect. It's like, this is close enough. Probably this is what it is. And that's his model, right? That's how he's thinking about the world. And you can go and test that model. All right. So we're going to grow some virtual pea plants, and that's going to be the goal. So like his hypothesis was like that. This is what's true about the world. 75% chance of purple flowers, 25% chance of white flowers. And we're going to test that. We're going to test that. And all a test is, right, it's just the idea. We were kind of talking about this last time. All it's showing us is like, what is the difference? Here's idea A, idea B about how the world works. Which one's the better one? All right, those are our hypotheses. All right, so a test usually chooses between two views of how data was generated, and those views are your hypotheses. It's usually like thing A happened or thing A did not happen. That's usually how your hypotheses work. So yeah, the test that you're going to do is going to give you firepower and give you proof to point you in the direction of one of the hypotheses. All right. The one that's better supported by the data. And here are the fancy names that I want to get us used to. So the null hypothesis, you'll hear this come up a lot. The null hypothesis is the one that we can simulate. Right? That's going to be something that's due to chance. You'll usually you read it as like nothing. Like the word null just kind of means nothing. Like nothing other than chance was the reason this all happened. That's kind of how you think about it. The null hypothesis is your chance model. That's how the book says it, about how the data was generated. We can always simulate that. So we can simulate a pea plant world where there's 75% purple flowers and 25% white flowers, and we can see how often we got like a little bit off from that. Yeah, like that's our null hypothesis. That's your simulated thing that's usually due to randomness, like it's a chance model about how the data was generated. The alternative hypothesis is the other one. That is the flip side of the null hypothesis. It's usually saying that no, the null hypothesis did not happen. It's your alternative, different view about how the data was generated. All right. So let's use these terms because I know they're a little weird. Let's use them in this example. So here, what we're going to do, we also need, sorry, before we get there, we're also going to need a number to point us at, right? That's kind of what we did last time too. We want some number that's going to tell us, like, was it more likely that the null hypothesis was the right one, or was it more likely that the alternative hypothesis was the right one? Because we need to know how close we are to each of them, right? And the closer to one, the more probably the farther away we're going to be from the other. And so that leads us to the idea of we need like some statistic that's going to tell us which side was the right side, all right? And that is called a test statistic. Hopefully that makes sense. That's a statistic that you choose when you're simulating to like point towards one of those hypotheses, which one you think is the right one, all right? So for Mendel, what we're going to do is we're going to simulate a garden of pea plants with this perfect 75-25 split, and we're going to count how many purple flowers. We could also have counted how many white flowers because it's like the opposite, right? It's just whatever's left. So we're going to count the purple flowers, and that's a number, right? That's a number that we can get back, and we're going to see how far away it was from his choice of 75% chance, because it was supposed to be 75% purple chance, right? 25% white flower chance. So we're going to make this our test statistic. What was the distance away when we make a sample virtual garden? How far away, what was the purple flower percentage, and how far away was that from 75%? So that's subtraction in absolute value. That's the distance away. Could have been above, could have been below. That's why the absolute value is there. So if you think about it, what we're going to do is we're going to simulate a bunch of virtual pea plants. And we're going to be like, all right, our garden was 80% purple. Our garden in this simulation was 65% purple flowers. And so if that's what was happening, this would lead to a test statistic of 80% minus 75%. Take the absolute value. That's like, that was 0.15 away, right? 0.65 is 0.1 away, right? Because it's 65% minus 75%. Take the absolute value. It's 10% away. So like those are our distances. And as we do the simulation, we'll see like how close like was it, right? So if our simulation really does reflect the real world, what's going to happen? Because that's our null hypothesis. Our null hypothesis is going to be like that. Mendel's model with 75-25 split exactly was right. If that's true, do you see how that's going to like, we're probably going to simulate like really close to 0.75, 756, 0.759, stuff like that. We're probably going to simulate really close to 75%. And that means our test statistic, if our null hypothesis is true, if that model really is generating pea plants that are really close to 75-25 splits, then small numbers from here, right? If we get small values out of this, are going to give us things that's going to point towards the null hypothesis, all right? So remember that the null hypothesis in this case is going to be there was exactly a 75% purple flowers. Any other difference was due to chance. Exactly 75% purple. Any other differences are due to chance. Okay, so that was the null hypothesis, and then the alternative hypothesis is the opposite of that. It's just saying like, all right, this model, this idea is wrong. It's not exactly 75% purple. There's something else at play for how the garden was picking the colors of the flowers, right? Not exactly 75% purple. The differences are not just due to chance. And I hope you see that numbers for our test statistic that are going to point towards the alternative are going to be numbers that are really like we'd simulate things very far away from 75%, right? And that's going to cause our statistic to be a large value. It's going to be a large distance away. And that would make us think like, okay, maybe our model's not that great. Maybe our model's not that great. There's something else wrong. Okay. So that's the difference. Does that make enough sense? Like we want some number that's going to point towards one of those ideas. And if this is the number we've chosen, do you see how if we define the null hypothesis as like exactly 75% purple flowers, then we would simulate, in theory, if it's a good model, close to 75%. 75 minus 75 is 0, right? So we'd have small distances, anything, something really close. All right. Large distances would tell us, it probably wasn't just chance. All right. So, all right, we're almost there. We're almost ready to go to code. So our goal now is we're going to simulate the test statistic, pretending that the null hypothesis was true, because that's the one that we can simulate. That's something that's due to just random chance. We can totally have a 75-25 split garden in code. We can do that. And we'll do a histogram, and that's going to give us the distribution of our statistic, again, assuming that the null hypothesis was true. If we do a bunch of simulations, then that will tell us what would have happened in real life. That will give us a really good approximation of what would have happened in real life if there really was an exact 75-25 split. All right. And then we'll see those, we'll compare those test statistics to the one that Mendel saw in real life and be like, did I see this one a lot? Was it just a little bit far away? Was it that far away under the simulated null hypothesis? If so, if this is something that it could generate, then that means it's all right. That means that the model could have been true. All right, it could have been true. We will accept the null hypothesis in that case. All right, so that's what we're about to do. I think the example will make it make more sense, but I wanted to say all those words first. Let's do that. It'll be very fun. So this is Gregor Mendel. So again, our empirical test statistic was this, right? This is what we found. It was 705 over 929, a little over 75%. We'll call that our observed proportion, right? And we can do this kind of statistic for that value that we saw in real life. We can do, it wasn't even simulated in this case. We'll do that same statistic. That's called our observed statistic. So our 705 over 929, let's do like times 100. So it was 75-ish%. And if we subtract Mendel's idea, it was supposed to be 75%. How far away was it? And then if you do absolute value, that's what we defined our distance calculation to be. That's going to be our observed statistic. Observed statistic is this. How far away from 75% was what happened in real life? This is our value that we got from the actual garden that he planted. So it was 0.88% away from 75%. All right. So now what we want to do is we want to simulate a garden. We want to simulate a garden assuming that this null hypothesis idea is true, where this is something we can generate, right? Exactly 75-25 split. We want to simulate that and calculate this same kind of statistic. How far away from 75 was it for our simulated garden, and compare against this number? Because if it was close in our simulations, that means that the model could have been correct. All right. So I would like you to try that now. It's going to be a call to sample proportions. So go back to the code that we were looking at, but here's my question for you. I want to pause and have you try. So try to use Mendel's model of 75% purple and 25% white to simulate a garden of exactly 929 pea plants. Again, you got to do the same number to get it right. And extract the proportion that were purple. All right, and my hint is use sample proportions. So try to generate a garden. Go back to the code from class from before. You can scroll up in this file that you have from last time. But try to generate the garden as exactly 75% purple flowers, 25% white clouds. We make that array of possibilities, right? Make that array of possibilities. And then plant a garden of exactly 929 of them, just like we did. And get back how many were purple out of those 929. So you'd have to go into the array that you get back from sample proportions, remembering which one was the purple one. So give that a try, and I want you to try it. All right. Did you see it? You see the idea for sample proportions? So the proportions for the flowers, 75, 25, you can make an array for that. 0.75, 0.25, right? And we can put the purple percentage first. We could have put it second. It doesn't matter, as long as you're consistent. And that can be our proportions for Mendel's model. 75, 25 split. And then for purple, right? So that's Mendel proportions. That was his. And then if you want how often it was purple, that's 75%, right? You get the first item out of that. But if you call sample proportions now, 929 pea plants with that model, do you see? That's going to tell you, all right, it made a garden of 929 pea plants with this setup. Randomly, with those weights, it found that there was a little over 76% purple flowers and a little over 23% white flowers. Does that make sense, how we're generating that garden? You just remember what was there. So 75.7-ish% purple flowers, 24.2-ish% white flowers. It's different every time. It's never perfect, but it's drawing from this set of proportions there. See that? So if you want the purple bit of that, you can do like dot item 0, right? Dot item 0. And if you just want the 75%, I could be like, what was Mendel's proportions for purple? 75%. You could also say Mendel proportions dot item 0. That would also give you 0.75, right? And so if you call your sample proportions, you're getting back how much purple, how much white. If you want to know how much was purple in your sample, you can just do it dot item 0, right? That was the very first thing you got back. There was a little over 75% for that one, a little over 70, almost 77% for that one. We go into the array that you get back for the purple bit of it. If that was the first thing, it's item 0, okay? And then the idea is, this is our simulated garden under the assumption that it really was a perfect 75-25 split. Everything else was just random chance. We want to see how often, we want to calculate that same kind of statistic, right? Or a simulated purple amount, subtract it from 75%, take the absolute value. How far away were we? Were we this far away? Because if we were, for our simulation, that means that our model can generate this kind of garden, that it's possible. It might just have been due to random chance after all. Nothing else was there. So if I take that and I say, I've got my dot item 0, that's like sample proportion of purple flowers, or the sample I'm just making right now. If I do the same calculation for my statistic, this is my test statistic now. This over whatever my sample proportion for purple is. Dun, dun, dun. And then we subtract Mendel proportions purple, or we subtract 75, honestly. We get that, okay? We get that. I guess I don't really need that here. Do you see how? Let's see. Whoa, I just got pretty much the same value. But if I keep rerunning this, I get different values for how far off it was from 75%. Yeah. How many percent off? This one was a little bit over, so it was even bigger than this value. So it looks like that this 75-25 split and this little extra bit could just be due to chance, because sometimes we're getting even farther away. So that kind of makes sense what's going on there? So we're simulating this garden just due to perfect random chance. 75-25 split. It'll never be perfectly 75-25 usually. It'll be close, but it won't be perfect. And we're going to see how far away it was. All right? How far away it was. So that's our goal. And so, yeah, kind of the next thing I want to do is, do we have time for that? How far are we going today? Yeah, I think we have some time. I want you to try some of these things, at least to think about them. You can ask questions, but I want to ask you to try one more thing now. I'd like you to do this, because we want to essentially generate a bunch of gardens, simulate a bunch of gardens, and get these test statistics back, comparing them to the observed statistic each time. So I'd like to make like a function that kind of does all this really quick for me. All right. So try to put that code into a function right now. That's my question. Make a function. We've been calling it like do one thing for me called, let's call it one simulated distance. To run a single simulation and calculate the distance from Mendel's model, which was 75%. So essentially, do exactly this, but put it in a function called one simulated distance. That would be good practice for our midterm. Can you do it? So you pretty much just want to do everything I just did in that cell above, because we want to give it a name, give that computation idea a name. We can run it a bunch of times. You don't have to write your answer. But you want to try to compare it to me. It's mostly copying and pasting, not putting it there. That simulates one garden, exactly how many plants he planted. It's how many were purple, the proportion of purple, and calculates our test statistic. How far away was that simulated proportion from 75%? So we subtract 75 and take the absolute value, because it could have been one direction or the other. It doesn't matter. It was bigger or smaller.
Sorry, not to interrupt you during lecture, but do you have a charger?
Just the one I'm using, and I don't think it's even USB-C.
Yeah, it's gonna be this one.
Oh, there's one baked into the desk. You might try plugging them into that.
That works.
Yeah. Nice. I think it's gonna bring your phone up on the screen.
I hope not.
Let me change it back to this. Come on, little screen.
If not, I can take the phone out.
Oh, that's all right. Let me try unplugging it and replug. Cool. All right. Yeah, here, that one shouldn't have taken that long, right? Just kind of, you give it a name, right? Say def. If it's going to be called one simulated distance, it's def one simulated distance. It doesn't need to take anything, right? It just does all this. It just does all this, and then it returns back that last answer, right? Returns back that last answer. How far away from 75% was this sample garden's proportion of purple flowers? Yeah? Does that kind of make sense of what it's doing? And we've decided that if we see small values for that distance, that means it was close, pretty darn close to 75%, 25% split. It wasn't perfect, but the differences were just due to chance, is what we're assuming. And if we get a value that was what we saw in real life, that distance was at least that. If we're simulating things at least this far away, maybe even more would be even better, that means that we are capable, right? That perfect 75-25 split is potentially the reason that explains what happened. It was just due to chance that we saw something this far away. All right. So our goal is to now call this function a bunch of times. You call it once, you get some distance, which is, this one's a bit larger than that 0.8 or whatever. We do it a couple times, that one's smaller, but that's good to know. And so let's simulate maybe 10,000 gardens of 929 pea plants. 10,000 repetitions. I want to save all the distances that I calculate. All the distances I want to save. Repetitions. I would like to np.append, right, to distances, this new simulated distance that I've made for myself. So this is going to make an array called distances of 10,000 different simulated gardens and how far away all of those were from, for their purple flowers, from 75%. So here are all those things that happen in the blink of an eye. Sometimes they're like, all right, it was 0.45% away, 1.85% away from 75%. So just due to sheer randomness, because that's how we're generating these, right? Just due to perfect randomness, we're getting values this far away, usually. And that's actually good news, these numbers that are above 1, because what we saw in real life, that distance was 0.88. Right? So maybe this is explaining why that happened just due to randomness. It didn't have to be something else. And so let's turn this into a table. Table with a column, call it like distance between sample percentage and 75%. I'll call that. I'll put distances there. And I'm going to get this table out of the deal. See that? It's all the different values for my proportions, for my distances. This is my sample statistic, right? Dists equals that. Oops. That's my dists table. And now I can make a histogram. So this dists.hist. That'll work. And that's kind of fun. Distance between sample percent and 75%. It's never below 0 because we took the absolute value, but these are all the different distances that we see. And the distance that we were calculating, if this is 1 right here, it was about 0.88, the one that we saw in real life. And so all of our simulated distances seem to be like covering that pretty darn well. So let's, I'm going to draw a little red dot for that as well. I'll change the title of the thing as well. plt.title, this is the prediction made by the null hypothesis. So now that gave me the title of that. I don't know why that is necessary, but I'll do it anyway. You don't have to understand what I'm doing right now. I'm just trying to draw a little dot on the page for our simulated, our observed value of our distance from 75%. This is what happened in the real world, Mendel's actual pea plant garden. This was this exact split. And how far away was that from a perfect 75? 0.88-ish%, 0.89%. So I want to put that value on this graph. There. So that's that red dot that I just added right there. So this is the distance between between the actual pea plant garden's percentage of purple flowers and 75%, which is what Mendel thought was actually happening perfectly. And these are all this is our distribution of simulated distances. Do you see how this value totally appears a lot? It totally appears a lot. It's covered by our simulation, which means it gives reason to believe then that our null hypothesis could be true, that really that it was a perfect 75-25% split like Mendel thought. Any difference between that was due to chance. Does that kind of make sense how we're noticing that? Because that's quite cool. That's quite powerful. And we can turn it into a number. Just looking at this graph, you can kind of tell, like, yes, this number, it totally appears a lot. That kind of distance, that's something that we get out of our simulation. It's totally there, but it would also be nice to have a number. So that number is, funny enough, called a p-value. So let's talk about it. So yeah, it's probably not good to just be looking at the histogram and being like, yeah, it's here, so it's pretty likely. Versus like if the real statistic was like out here, that means it wasn't really predicted by our model. That's kind of like hand wavy and not good enough. So it's better to use a number, and the number that we're going to use is called the observed significance level. For a weird reason that I don't fully understand or remember, they call observed significance level p-value. All right, it's a percentage, I guess. Maybe that's why it's a p. But what the p-value is, if you look it up in your book, let me just read the fancy definition. It is the possibility that you saw this, essentially, in your chance model. It's the chance based on the model in the null hypothesis, the one that we generated, that the test statistic, the number that we chose to decide which hypothesis was the right one, will be equal to the observed value in the sample or even further in the direction that supports the alternative. That's key, and we'll talk about that, all right? So what is the possibility that this value that we saw in real life was generated by our null hypothesis chance model, all right? And we get back a percentage when we calculate the p-value. If your p-value is small, that means your null hypothesis model didn't really predict that value occurring very often that you saw in real life. So a small p-value supports your alternative idea. Like, okay, yeah, it wasn't just due to chance. In the real world, maybe you've heard about this, but less than or equal to 5%. That's usually for a p-value. Like if your value is predicted only less than or equal to 5% of the time, that's called statistically significant. So it's 95% chance it wasn't predicted, right? And less than or equal to 1% is called highly statistically significant, okay? So that's where we're going. And so the idea is, we want a number, right? We want to know like how likely was this value that we saw in real life, this distance away from 75% in like Mendel's original garden. How far away was that, or how often did that occur in our simulation? And so what we can do is we can say, all right, here are all the distances that we simulated, right? Assuming that it was a perfect 75-25% split, here were the distances that we simulated. How often was it equal to the observed one, that 0.88, that thing that Mendel saw in real life, or even more extreme? How often was it that, or even more extreme, which would be in this direction, right? Greater than. How often was it this way, or even farther away? Because we thought that a large distance meant that it wasn't a good idea. So how often was it this, or even farther away? How many times? So we get a bunch of trues and falses. You can do np.count non-zero. How often did we see a distance that was bigger than or equal to our observed distance? 5,515 times, apparently, which is a decent number. And if we divide by how many times we did all this, by our repetitions, how many times we took a simulation, we made a simulation, this gives us a p-value, this gives us a percentage of how often did we see a value that looked like the one that we got in the real world, or even farther away that made us think differently, right? How often was it this, or even more extreme, so bigger than or equal to, over 50% of the time. You see that? So that means that our model, 55% of the time, it does give us a value up here or even more extreme. And so that means that our model might be correct. Does that make sense? Like over half the time, if it was a perfect 75-25 split, you'd see something that far away. You would totally see something that far away. And that's really powerful. That is our p-value. All right. That is our p-value. And let's see here. How do I want to say that? The idea of the p-value, it's kind of like an area, if you think about that. So pretend that like this is the distribution, this histogram is the distribution of all the different test statistics that we were simulating under our null hypothesis. The idea that it was just due to chance, whatever happened was just due to chance. Pretend that the red point was what we saw in real life. Our empirical, what do we call that? Our observed empirical statistic. And let's say that the values that we care about is like, was it this or even more extreme? Maybe more extreme sometimes means it was a smaller value. All right, so that's the thing. And so kind of what we're doing when we're calculating the p-values, we're saying, all right, how often was it this value or something even more extreme? And we're adding them all up. It's kind of like an area we're taking. Like what's the proportion of the yellow to everybody? How often was our model predicting what we saw in real life? Because if it predicts it sometimes, like enough times, that means maybe our model was the correct model, like that. It was just due to chance. It was just due to chance, and it was okay, and our model was correct. Okay? And our model was correct. So does that make a little bit of sense? Any questions about that idea? Because, again, what we've done is Mendel was like, all right, I saw this exact proportion of pea plants, but nature probably doesn't work in 0.7589% of the time. Nature probably works in 3/4%, right? They're like, all right, it was probably a perfect 75-25 split, even though we saw this. And so we came up with a number to describe how far away this was from 75%. That was our simulated, our test statistic. Subtract the absolute value. And our null hypothesis was that, yeah, it was a perfect 75%, 25% split. We were able to simulate gardens with that split and see how far away they were from 75. And we saw quite a few gardens that were this far away. The more we saw, the more likely our model is correct and capable of predicting what we saw in real life. And that gives us confidence that it really was just due to chance what Mendel saw. It was a perfect 75%, 25% split. All right? But what if it wasn't? Here, let's say that we had some different observed statistic. Let's say that we saw, like, Mendel in the real world, he saw the values, he saw 78% or something. It was 3.14% away from 75. Let's do the same thing. Just pretending that was true. Different. Boop. So he's over here. Pretend that was what happened. We're again assuming that we saw a perfect 25%, 75% split. That's what we're generating in our simulation. But let's say that in the real world, Mendel saw this distance away. It was like 78 point whatever distance away, 78.14 or whatever. He saw something like that. And so our question is, how often does our model predict a value out here? Because if it does it often enough, then maybe our model still is correct. But this one's more unlikely, right? It's more unlikely for our model to predict this value because it's like, how often was it here or something even more extreme? Not very often. Not very often. We can do the same p-value calculation. And this time it's different observed statistic. How often did we see a value that was equal to the observed statistic or even more extreme? More extreme for us means farther away from 75. Less than 2% of the time, or yeah, less than 3% of the time, almost 3%. So that means that if this were our observed statistic, it's like, all right, it's pretty unlikely. Sometimes our model does predict it, but it's not very often, so it's probably not the world's best model. This is a statistically significant issue. Yeah, and so that kind of makes us think that, okay, maybe it was the alternative hypothesis that was true. Something else was at play here. All right? So that idea makes sense. You're taking that number that you're using to like see if your model was a good model. You simulate a bunch of stuff due to chance, you plot what the thing was that you saw in real life, that version of your statistic, and then you ask the question, how often did I simulate that value or something even more extreme? If it was a very small percent of the time, sometimes it was 0. Last time it was 0, right? We were secretly doing that last time too. If it was so small, then it's likely that your model isn't right. There's something else at play. More could happen here, all right? Yeah. Questions about that example? It's a long example. Does it make enough sense? So you read more about this in the chapter, of course. But yeah, this is us getting a number. Our p-value is like, how often did our model predict this thing? It's kind of like an area. And it's going to tell you if you think that the null hypothesis is correct or not. All right. So there are ways to make mistakes, of course. It's possible for you to just like get really unlucky. You can still be wrong when you're concluding stuff, like you're saying that, oh yes, I believe in the null hypothesis, or no, I don't believe in it because the number was so small. You can still be wrong, but at least there's a way now with our p-values to quantify our uncertainty. So if the null hypothesis is true, what our p-value is saying is there was a p% chance that our model would say this thing, right? So there's a p% chance that you would think the opposite too. So if the null hypothesis is true, that's equivalent to the idea that our model is correct, right? That means that our model is correct. There is a p% chance that you incorrectly concluded that it's false, right? Because if you saw, it's like, all right, 3-ish% of the time our model does predict it. Maybe we just got really unlucky and like, yes, it is possible. It's just very unlikely. Our model is still correct, but we might be like, you know what, probably it wasn't because we saw such a small number. So there's a p% chance, right? So our model does predict it sometimes. There's that percent chance that we were wrong. All right, that is this idea where like the null hypothesis really was true, but our test was in favor of the alternative because we saw such a small number. It was so unlikely to predict it. So that's this idea, this error. All right, that's a certain kind of error. There's another kind of error where your alternative hypothesis really is true, your null hypothesis is wrong, but your test didn't give you a small enough p-value. And so you're like, all right, I still think the null hypothesis is true. So that's another kind of error, but that's a different kind of error. All right, that one's a bit more complicated to talk about. Maybe we'll get to it later. But one way to deal with error is to use a larger sample size. The more you use a larger sample size, the smaller the spread is between values. Things get tighter together, and so that's very hand wavy. But that's one way to like deal with this. When in doubt, use more simulations. Okay, so I think I have one more example to talk about this stuff. Are we ready to go through that one? It's another worked through example. But it will give us some more practice with this idea of like null hypotheses, alternative hypotheses, finding p-values, figuring out what a statistic should be. It's a lot of stuff that you need all at once. I know, it's a little weird. But remember that the null hypothesis is the one we can simulate. That is assuming that all of our data that we saw was generated in a very easy to generate way, perfectly randomly. We can simulate it. The alternative is kind of the opposite. It's like, all right, there was something else at play. I'm not sure. But it wasn't the null hypothesis, probably. I saw a very small p-value. All right. So here is the last example I want to do today, I think. Yeah. Let's say that you're about to take the midterm, so this is perfect example. Let's say that we've got a pretend class. The book made up some numbers. We've got some midterm scores for like a physics class or something. I don't know. Let's say that students in a class, they took a midterm, and the midterm is out of 25 points. All right. And then here are the scores. All right. And there's a situation going on. There's a mystery that we're going to solve. It's in scores. Scores by section.csv. That's my sample data file. So it's called scores. Boop. And what we've got in this table is a bunch of midterm grades out of 25 is the score, right? So scores out of 25. Then you have a bunch of sections. And what section is a lab section. Maybe you've taken a class where this is true, right? But maybe not here, but at a lot of four-year schools, like lab sections, they're not like run by the professor. They're run by a TA usually, not by the instructor. And so maybe if this was like a physics class, like some of the students, they took their exam in their lab section. Or they all took it in their own little lab section. There were a few different lab sections, like section 1, section 2, section 3, and a bunch of different students scored there. Okay? So, yeah. Section 3, with this sample pretend data, section 3 did not do very well. All right? Section 3 did not do very well. And we want to ask the question, like, is it the TA's fault? All right? So that is our question right now. What I'd like you to do is, I guess, this would be great. A great review for the midterm. So here's a question I want you to try. So try to read this data. It's in scores by section.csv. Get that into a table. And what I'd like you to do is get the average midterm scores by section. How many different sections are there? There's apparently 12 different sections. Let me prove that to you. Scores dot column 0. So there's all the sections. The biggest section is section 12. But there, you shouldn't have to deal with that. Try to get all these scores, get the average score on the midterm by section. So section 1, what was the average midterm score? Section 2, what was the average midterm score? Section 3. You remember how to do that? It's something on tables that you can use right now. So try to remember that. Haven't tested hypothesis. It's just us exploring the data. It's totally something I'm going to do. Try to get the average score for section 1, section 2, section 3, all those bad boys. Just like that. Give it a try. I'll give you another minute to think of it. It's an action on tables that would do this for us. Because you got a bunch of different sections. Remember how to aggregate? That's the fancy term, right? You want to aggregate by section, the average. Remember what you could do there? All right. What was it? Scores dot what? Group. Good. And we're going to group by the section, right? Group by that section. By default, it'll just tell you how many people were in each of the sections. Like, all right, there were 32 people in section 1, 32 people in section 2, 27 people in section 3, 30 people in section 4. But if we do something else here, we can say, all right, when you're bringing together all the section 1 people, when you're bringing together all the section 2 people, don't just count how many things are there. Apply this function to all the values. What function do we want to apply? np.average. So there's the first 10. If we want everybody, it's dot show, not table. But does that make sense how we're grouping by section? It's bringing them all together. And it's giving us the average scores per section. So there's a bunch of people in section 7, their average score on the midterm was this. Same with all the others. Does that make sense? That's a good review, I think. Dun, dun, dun. Yeah, so remember that if you just said group without anything, you get the size of stuff. So that's a thing. Dun, dun, dun. So that show. So these are the sizes of all the sections. Look at section 3 now. Do you see how section 3 performed the worst? Section 3 performed the worst. Everybody else did better than section 3. The question now is, was the TA in that section doing a bad job at teaching? Yeah. Compared to the other people, the other TAs who are leading the other 11 sections. All right, that's the question. Is the TA in charge of that section to blame? We can formulate this as a test, all right, with a null hypothesis and an alternative hypothesis. Can you kind of see how we're going to do it? Because the null hypothesis has to do with something with chance. So if we're asking about section 3, do you see how something involving chance could just be saying, like, all right, section 3 just happened to do poorly. Just by random chance, the average score of section 3 was no different, right? It was, how big was section 3? It was, there were 27 students in section 3. We just got a bad batch of 27 students. That's our null hypothesis. Just randomly, if you pick some random 27 students, sometimes they'll do this poorly. Does that kind of make sense? That's something that we could simulate. The average score of section 3 is no different than it's from some other random selection of 27 students sampled from the total class. Does that kind of make sense? That can be our null hypothesis. We can be like, okay, all the sections were generated randomly. You just like give me some random section. You'll find some with a grade that small. All right. Our alternative hypothesis would be turning that on the other way, on the flip side. So the alternative hypothesis would be saying like something like, okay, there was something special about section 3. Maybe it was the TA's fault. It wasn't due to just pure randomness. The average score is lower than we would expect from some random bit of 27 students taken from the class. All right, there's something other than randomness that caused the low average, perhaps the TA. All right, does that kind of make sense? Those two ideas. You see how the null hypothesis is something that we could simulate? Just like go and pick, because we got all these scores, right? Forget about the sections. Just go and pick 27 random scores. That's a sample section. Go see how often, right, we saw an average this small. Because if it's possible, if we see that a lot for just some random section of the same size, then maybe it wasn't anybody's fault. It was just happened to be randomly a bad performing section of students. Okay, it happens. So that's our question, right? Was that true or not? Okay, so are we ready to test it? I want to generate now some things. So let's get our actual empirical values, right? Our observed things. So we've got the section 3 average. It was 13.6667, but you could also just be like, do the thing. Go and get section 3 column. Go and get the column for, what was it? Midterm average. And then get me the third thing, so 0, 1, 2, right? That's the third thing. That's the section 3 average. Then the size of section 3, it was 27. You can just hard code that if you want, or you could just be like group by section and do the same stuff. Just get the size of the third thing. So that's section 3 size. All right. So those are the values. Midterm average. Did I spell something wrong? I must have. Section and p to average. Oh, sorry, this one's just count. There we go. So yeah, we've got our 13.6667 and our 27 here. So we got those things. And now the goal is we've got just the entire scores of everybody. Right? We've got the scores of everybody in our scores table. I want you to try this. It's good to pause and try. So here's my question for you again. Try to simulate now a section with the same size as section 3, by picking random students. All right, random students, and get the average score. Okay, so go and pick 27 random students from this midterm column, right? Does that make sense? Go and pick that many students and make a class size of 27, the same size, and get the average score of that class. Does that kind of make sense? What you shouldn't do, remember that there's two different ways of sampling, because that's what you're about to do, right? You're going to sample from this table. What you shouldn't do is don't allow any students to be included multiple times. Because you don't just want to like take 10 versions of this person. There's only one version of this person in the real world. So you shouldn't allow any duplicates, right? Because then you'd be picking from not the same students. You'd be cloning students, and that wouldn't make sense. Remember, we have to go back to the documentation, but you're going to take a sample from either that column, right? Or from the table itself. There's two ways to do it. Go to the column first, or go to the table first. And then get 27 different students. That's your simulated class of that size. Get their midterm scores and take the average of them. This file is called scores by section. So this is a good review of taking samples. I'll give you a few more seconds of a head start. All right. So there's a couple different ways to take this sample, right? You could do, remember our options? We could do np.random.choice from a column, because the column is your array. And then you'd have to say without replacement. Replace equals false. Don't repeat people. Replace equals false. So that's the first way to do it. The next way to do it would be to do it on the table itself. You have your table, you say dot sample on the table. How many rows do you want? And then again, you'd be like with replacement equals false. Because don't duplicate any students, don't clone any students. I want to take from the current population of students, not duplicating anybody. That would be making up grades. Take the same grades and the same amounts, please. All right. So yeah, there's a couple different ways to do that. We can do, let's do it with the table-based way. We can be like scores.sample. I want to sample exactly as many people as were in section 3, 27, or I can use section 3 size because I already have it. And then I want to say with replacement equals false. Do not replace anybody, please. And this will give me 27 random rows, right? People from other different sections is fine, but I've got 27 random rows of my table, no duplicates. And I've got a bunch of midterm scores for all those different students. Now, this is my simulated section 3, all right? Random section. equals that. And what I want out of this section is the midterm column, right? Go there. Give me that midterm column and take the average. This is an average. This is the score for this random set of students. Their midterm score, it was average 13.96, which is honestly not that far away from this section score. We randomly got that, so maybe that's good news. I don't know. So that's part of the question, right? That's part of the question. We want to do this a bunch of times, though. We want to keep on doing this. We want to keep on saying like np.average, some random section, and their midterm column. If I do this again, it's just be like, do all that, right? That's me getting a random section all over again. Scores.sample. If I keep on doing it, this is a bunch of different simulated section 3s, right? Same size as all of them. What was the score that we got back? You see that? Does it make sense how I'm doing this? This is a random section of students and their midterm scores. I want to see how often do we simulate, right? Because this is just due to pure randomness. How often do we simulate, if it was just due to randomness, a score this low or lower, right? Something more extreme. How often does this happen under our null hypothesis model, the one that we're generating due to just pure random chance? Because if it happens a lot, then it probably was just an unlucky TA. They got a bad group of students somehow. Yeah. So this, I want to make 10,000 of these essentially, right? I want to do a bunch of these. Let's make a function that does one of these simulated sections and the average grade for them. So def1 simulated average. It's just this, but return it, right? And so if I call it one simulated average, every time I get back some new number. Now I can make a big long array of all these things. Yeah, big long array of all these things. Let me give you all this code, because I want you to try that. If you refresh our code from class, you should have everything I've just typed so far. But my question for you, maybe one last time, is, let's see. Yeah, this is probably the last question of the day. Try to simulate 10,000, just like we did above. You can scroll up, averages, using our function that we just made, into an array called sample averages. Okay? Into an array called sample averages. So try to run that function 10,000 times and save, because you're making a bunch of random section 3 students, right? And getting their average midterm score. So get a bunch of random students' midterm scores using that function and fill up an array. Our goal is to see how often out of those 10,000 times did we see an average that was as small as the real life section 3. Or even smaller. That would be even more extreme. But this is just letting it be due to pure chance. Pure chance. So you could probably copy and paste a lot of stuff that we did before. But if you get it, try to make a histogram before I do. Give you another minute of a head start. No, I did forget to do that. All right. So I will legitimately copy and paste as many things as I can. So I kind of want to do all this again. 10,000 again is a good number. It's a decent amount. We can do it pretty quickly. Oops. Now, you don't have to call it repetitions. You can call it simulations as long as you're consistent and you use that where you need to. And we're going to call this sample averages, right? Sample averages, and it's one simulated average. That should honestly do it. And then sample averages is a big long array now of a bunch of average scores for perfectly randomly chosen section 3s. Yeah. And we're seeing the average score on the midterm of those students. Yes? Does that make sense what we've done? Because now our question is, all right, this is the score that the real section 3 had. How often did we simulate that? Because if it was just due to randomness, that we'll see that in our simulation because our simulation was due to randomness. And therefore, maybe the TA isn't really to blame. It's just like they got a bad group. Who knows? So let's turn this into a table because then we can turn it into a histogram. Table with column. Random sample average. And sample averages goes in there. Of course, so there's my big long table. And I'll call that averages table. There's my table. I gave it a name. And I can say, give me a histogram of that. And for fun, we can give it like, do a bunch of bins. Do 20 bins that you generate automatically, please. So here are a bunch of random sample averages. And the one that we had was, our average score for section 3 was 13.7-ish. It was around here, maybe? Let's plot it on the graph. You don't have to learn how to do that, but I'm going to do it for us. So section 3 average. So you don't have to understand that line, but there, I just put a red dot where that average value was that would happen in real life. And so do you see how our model of like, all right, let's just like pick some random students. Let's pick random students, generate a random section 3, and get the average score. You see that we sometimes really do have, we see that score a decent number of times, right? We're simulating it this many times, or even something more extreme in a smaller grade, right? Due to just pure randomness, picking out some students, we get this one, we see this number a bit, as well as things smaller than it. It's not impossible for our model to generate that. So now the question is, what's the percentage? So out of 10,000 times, how often did we pick a random set of students and get and have an average grade for their midterm scores be this or even more extreme, right? How often does our model predict this or even more extreme? And so that's saying, like, how often was our sample averages values equal to the section 3 average, the real one, or something even more extreme, which is smaller in our case, a worse grade, right? How often did that happen? So np.count non-zero. It happened 559 times, and then we divide by how many simulations we took, and I call that simulations this time instead of repetitions. or you just type over 10,000. And so this is our p-value. Our model predicts that if it was just due to pure randomness, we would get students with grades this bad or worse. If we were just picking students randomly and putting them into sections, this would happen about 5.5% of the time. Does that make sense? So our model is predicting that. That's our null hypothesis. And so the question is that, what does that mean, right? If we go back to our slides, like a lot of people, they're like, all right, if it's less than or equal to 5%, like that's your cutoff for the p-value. Then it's like significant, statistically significant, only less than 1/20th of a chance do we see this ever happening by our model. But we saw something a little over 5%, right? So we would say that it was not technically, according to the definition, statistically significant. A little over 1/20th of the time does our model give us a class with a score this bad. Yeah. So that doesn't mean that our model's wrong. That could point to the idea that, okay, maybe it's unlikely, but the null hypothesis does go to show that this is possible. The TA in charge of section 3 could have gotten unlucky, and we're just accusing them for no reason. Okay. So I guess the question is, this isn't statistically significant, but like, what would you do if you were the teacher? Maybe this doesn't point to like, okay, it's somebody's fault, but you'd probably want to go and look at that section. Now you want to go and observe, make sure that like this would give you reason to go want to evaluate that TA or something, probably. So it's possible that they just got a bad batch, but it only happens apparently less than 6% of the time. So are we within that universe? Maybe, but it's more likely that we aren't. Does that kind of make sense? How you're thinking about things and you're coming to conclusions based on these numbers that we're generating here. So our model is something due to randomness. We just picked some random students. That was our null hypothesis. Oops. But the average score was just no different from a random section of 27 students. That's how we sampled and simulated. And technically, it sometimes this happens, but there's no right answer here, right? I guess the answer is we need more data. Go do it again. See what happens for the next midterm. See if there's a pattern. Okay? So I think that's what I wanted to say. So the moral of today's story is if you want to test something, you have to come up with two hypotheses, one that you can simulate and one that's kind of the opposite of that. Like, okay, something else was going wrong. It wasn't just pure randomness, because the simulated one has to be due to pure randomness. You come up with some number that's telling us which hypothesis is the more likely one. For I guess for this one, it was just like, what was the score of that random section? And then for this one, it was how far away from 75% were the purple flower percentages. Those were numbers that we could tell, like, okay, if I saw these kinds of values, it meant this. If I saw these kinds of values, it meant that. And then you do a bunch of simulations. You do enough of them, you can have some good ideas as to how often the value that you saw in real life, your statistic value that you saw in real life, really happens according to the model that is implied by your null hypothesis. And then if you calculate a p-value, that's telling you how often did you see a value that was that or even more extreme. And if your model can sometimes generate that enough percent of the time, like over 5%, for the other one it was over 50%, right? Over 55% of the time did we see something, that value or more extreme, then that means your model is probably a good model. That means that maybe you did have it all right. It was just due to random chance, all the stuff that you saw. You do not, you accept kind of your null hypothesis. In the literature, they say, we do not reject the null hypothesis. The p-value isn't small enough. So that's kind of what's going on there. But yeah, there's a lot of words. It was a bunch of examples. It's worth remembering and studying. But I think that's all that I wanted to say for this chapter today. We'll do the rest next time. Are there any questions about anything that we talked about here? Because I have one more thing to talk about. Do also remember we've got a midterm, right? We're not going to forget about the midterm. It's in this class in 1 week. Okay? 1 week, you got to take it on the big computers in the room. And class. The last thing I want to talk about before I let you go off and work is every semester, even though I'm not like being evaluated by the school this semester. Sometimes that happens though. I like to give out a little feedback form for my students. It's called mid-semester anonymous feedback. And it's not for a grade, of course. It's perfectly anonymous. But if you'd like to fill it out, I'd appreciate your input. It's just an anonymous survey on Google Forms. So it's like, here's the kind of questions that I ask you. You don't have to fill it out if you don't want to, but if you do, I will totally read it. This is like, because we're about in the middle of the semester, we're in week 8, and there's like 18 weeks of the semester, so it's close enough, because we got the midterm next week. So I don't want to do that. It'd be too many things all in one week. So we're about in the middle of the semester, so you can give me some feedback right now, just perfectly anonymously, and that will help me. Like, if there's something that's going wrong in the class, you can tell me about it while you're still a student. We can make it right. So, yeah, here are the kinds of questions that I ask. Like, give me 3 things I should keep doing, stop doing, start doing, and a couple other things. What would you want to change anything about the class? What could it be? This will help me help you as well as my future students. So I'd appreciate your input if you have any. But obviously, I can't tell if you respond. You don't have to do it at all. But yeah, that's something that I like to give out, just if you're interested in giving me some feedback. And yeah, that's, I think, all that I've got. So next week, we're going to review for the midterm during our one Monday normal class. And then on Wednesday, it'll just be a day for the midterm. Okay? It'll just be time to do the exam. And that'll be it. So yeah, that's all I want to record.